Hello, first of all, I thank you for watching this video on AI recognition design. This video represents my passion for research and design in the field of AI recognition. Therefore, my AI recognition design is encapsulated in this summary video. I sincerely hope that this video proves to be beneficial to the viewers. Prologue. Recognition begins with assigning names to samples, based on human definitions, and organizing similar samples under these names to improve understanding. The sample name recognition path plays a pivotal role in recognition, as it enables us to identify unknown samples by leveraging these pathways. We select the name of the most suitable recognition pathway for the unknown samples. As intelligence grows, recognition evolves from sample grouping and labeling to establishing more structured recognition paths and scopes. I embarked on research to design AI recognition systems based on this understanding. Recognition principle. Think of intelligence as building blocks. Each block represents a concept formed by assigning a name to a sample. To strengthen initial intelligence, we can link more samples with the same name to the concept. And to deepen it, we can connect different concepts in a structured way, like a hierarchy. Step 1. Recognition path to recognition scope. To specify the enhancement of initial intelligence, I consider a one-to-one mapping of one label to one sample as the fundamental recognition path. This figure illustrates how repetitively mapping similar samples to the same label reinforces a recognition path, expanding the recognition scope from one-to-one to n-to-1 as more training samples accumulate over time. Step 2. Recognition path to recognition depth. I establish recognition depth using a hierarchical structure with 3 levels of labels. The figure illustrates how the recognition path transitions from a one-to-one to a one-to-many mapping when employing 3-level labels for the same sample, offering a diverse approach to object recognition. Higher-level labels encompass lower-level labels, resulting in broader recognition scopes and mapping more samples. Thus, the gradual recognition from grandparent to parent and child levels, as depicted in the figure, is vital. Step 3. Outside AI scope and AI with epoch. The figure depicts a scenario where I intentionally picked random samples from a group labeled vehicles to create dataset A1. Now, let's delve into when the recognition scope AI A1, derived from dataset A1, fits within the inside scope, and when it falls outside the scope. Inside AI scope indicates how well AI A1, as shown in this figure, recognizes sample A2 from subset A, not dataset A1, as fitting within AI A1 scope. Depending on the method used to measure similarity, and the applied threshold values, sample A2 might not be deemed similar. Nonetheless, the goal of this study is for AI A1 to accurately classify sample A2 as belonging to the same category. Outside AI scope refers to when the AI encounters samples from a different subset. For instance, in this figure, if AI A1, trained on dataset A1 with vehicle samples, assesses a sample B1 from subset B with food samples, it falls outside the AI A1 scope. Without metacognition, AI A1 cannot recognize sample B1 as outside its scope. Therefore, defining the outside AI scope and detecting samples outside AI scope are crucial for accurate AI recognition. My study concentrates on metacognition AI identifying such instances that fall outside AI scope. This prevents misrecognition, such as sample B1, through epoch, halt judgment, and integrates them into future retraining efforts. Step 4. Softmax-based post-sample identification. The figure displays a recognition scope centered on vehicles. During test sample recognition, the AI evaluates different scopes quantitatively, selecting the one with the highest value. However, there may be instances where the AI misclassifies a motorcycle image as a vehicle, indicating a limitation. After the AI identifies the appropriate scope and assigns a label to a test sample, it's crucial to decide whether to accept or reject the outcome. To avoid erroneous outcomes resulting from insufficient training, Softmax quantifies confidence probabilities in recognition results, as depicted by the 66% prediction confidence in the figure. Step 4. Softmax based outside AI scope. Through the following deductive reasoning process, I define test samples with a maximum softmax probability of 0.95 or higher as inside AI scope. 1. Samples with a softmax probability of 0.95 or higher are considered inside AI scope. 2. Such samples ensure very high prediction accuracy within the AI scope. 3-to-1, consistently, selecting these samples in a test dataset yields higher prediction accuracy than the overall accuracy. The figure illustrates prediction accuracy categorized by each confidence range and 3 models. Notably, the blue charts within the green box, 0.95 or higher, exhibit higher accuracy than the overall prediction accuracy. 3-to-2, additionally, when multiple AI models from distinct training datasets converge on test sample selection, the prediction accuracy of the chosen samples exceeds that achieved by a single softmax model-based selection. The graph displays prediction accuracy across different softmax confidence ranges for 3 models. Particularly, the blue bars within the green box, 0.95 or higher, signify higher accuracy than the overall. When comparing prediction accuracy between the single softmax model and the lowest value among the 3 models, the latter outperforms the single model. Epilogue. My AI recognition design emphasizes recognizing only confidently identifiable samples based on training data. Both humans and AI encounter challenges in recognizing or judging numerous unspecified samples with limited training data. Therefore, when faced with samples beyond the recognition coverage, embracing a learning attitude after shouting "eposh," instead of making immediate judgments, can elevate intelligence to the next level.